Hello dear students, so today we will talk about the next topic of unit 4, that is the CMOS logic family, which stand for Complementary Metal Oxide Semiconductor logic family, and this uses both p-type and n-type MOSFETs. Okay, so therefore the MOSFETs, they are designed basically to have a matching characteristics, which means that they can exhibit identical characteristics in switch off as well as in switch on conditions. Okay, so basically the main advantage of CMOS technology is that it lies in its extremely low power dissipation, okay, which means that nearly zero in static conditions. So why they draw low power? Because they only draw power when they are in switching condition, in switching mode only, then they draw the power. Okay, so now we will discuss the different parts of CMOS, that is CMOS as an inverter, CMOS NAND and CMOS NOT. So first of all we will discuss about CMOS inverter. You can see here the diagram of CMOS inverter. So now I will be describing the diagram. So basically the inverter, you know, it is the most fundamental building block of CMOS logic. Okay. So now you can see the diagram. It consists of pair of N channel and P channel MOSFET. They are connected in cascade configurations. So you can see here the arrow, the functions are as follow. As you can see, if the arrow is outwards, then it is P channel, and if the arrow is inwards, then it is N channel. Okay, so when we give the logic, when the input is in the logic high, that is in the high state, I will tell you. Here you can see the input. If it is on logic high state, that is 1. Then the P channel MOSFET Q1, that will lie in the cutoff state. Okay. And while the N channel MOSFET, that is Q2, they will lie in the conducting state. Okay. So the conducting MOSFET, they will provide a path from the ground to the output, and the output is low. That is the output will be logic 0. Okay, here can the output will be logic 0. So when the input is in the low state, that is logic 0, if the input will be in the logic 0 state, then what will happen? Then Q1 will be in conduction and the Q2 will be in the cutoff. Okay, so the conducting P channel device, they will provide a path for VDD. You can see it will provide the path VDD to appear at the output. Okay, it will, okay, are you understanding that it will provide the path VDD to appear at the output, so that the output will be high. That means that if it is input is 0, then the output will be logic 1. Okay, so the floating could lead to the conductions for both MOSFETs and a short circuit conditions. Okay, so it should be therefore avoided. Did you understand? So we can also say, as you can see in this figure, that there is no conduction path between the VDD and the ground. You can see there is no conduction path, okay, in the VDD as well as in the ground of the input condition. So therefore when the input is logic 1 and logic 0 and the 0 states, that is why there is practically zero power dissipation in the static condition. Did you understand? As I have told you that is power dissipation is low. So this is the reason, because there is no conduction path between VDD and the ground. So due to this, if the input, when the input is in logic 1 as well as in logic 0 state, then there is practically no zero power, that is no power dissipation in the static condition. So this is the only dynamic power dissipation which occurs during the switching operations, as the MOSFET gate capacitance is charged and discharged. Okay, so the power dissipated is directly proportional to the switching frequency. Okay, so it is completely dependent upon the switching frequency. Okay, so now we will talk about the NAND gate. Now I will show you about the NAND gate. Okay, so here you can see the diagram of the NAND gate. So here in the figure you can see the basic circuits of implementation of 2 input NAND gate. Okay, so as you can also see in the figure that there are 2 P channel MOSFETs, that is Q1 and Q2. Okay, I will mark them. You can see here Q1, this is the Q1 and this is the Q2. Okay, these are the P channel MOSFETs. You can describe by the arrow, and they are connected in parallel with the VDD. You can see they are connected in the parallel with the VDD and the output terminal. Okay, so and the 2 N channel MOSFETs, you can see here, that is Q3 and Q4. They are connected in series with the ground. Okay, so in series they are connected with the ground, okay, and the output terminal. Okay, so the circuit operates, I will tell you how it will operate. So for the output to be the logic 0 state, now if we want it is essential that both the series connected N channel devices should conduct, and both the parallel connected P channel devices remains in the cutoff state. Okay, so you are you getting? So this should both the, as I've told you that both, if we want the output to be in logic 0, then it is essential that both the series connected, these are the series connected N channel, they should be in the conductive mode, and they should be in the the P channel MOSFET, they should be in the cutoff state. Okay, so only then it is possible that both the inputs are a logic 1 state. Okay, so this verifies that one of the entries of the NAND gate truth table. Getting? So when both the inputs are in the logic 0 state, then what will happen? Then both the N channel devices are non-conducting, and both the P channel devices are conducting. It means vice versa. Earlier which was that, now it is opposite to that. So which will produce a logic 1 at the output. Okay, then we will get the logic 1 at the output. Okay, so this will verify? This will verify the another entry of the NAND truth table. Okay, you might be recalling the NAND because I have discussed NAND truth table in previous videos also. Okay, so now for the remaining two input combinations, now actually if now the last two inputs combination, so for the remaining two input combination will be if either of the two N channel devices will be non-conducting and either of the two parallel connected P channel will be conducting. Okay, so then what will happen? Then we either have Q3 off and Q2 on, or we will be having Q4 off and Q1 on. Okay, so the output in both the cases will be logic 1. Okay, which will verify the remaining entries of the truth table. I hope you understand all the characteristic input entries of the truth table. So this was about the NAND gate. Okay, now we will talk, now the next is the input to input NOR gate. Now we will discuss about the NOR gate. Now you can see in the figure that it shows the basic circuit implementation of two input NOR. Okay, so now in the figure you can see there are two P channel, wait, let me mark you. So there are two P channel MOSFETs. Okay, you can see which are the P channels, as I have told you, Q1 and Q2. You can describe with the arrow that which are the P channel, and now the two channel MOSFETs are Q3 and Q4. Here you can see, and they are connected in parallel with the, first of all, the Q1 and Q2. We will discuss about the Q1 and Q2. The Q1 and Q2 are connected in series with VDD, you can see, and the output terminal. Okay, and the N channel MOSFETs, they are connected in parallel between the ground and the output terminal. Okay, so now the circuit will operate. I will tell you how it will operate. Now first of all we will assume that for the output to be, if we want the output to be logic 1, then what will happen? So it is essential that both the series should be connected. What does it mean? That why it is, if we want logic 1 to be output to be logic 1, then it is what it is essential that both the series connected P channel devices should conduct. Okay, and both the parallel and connected devices channel should remain in the cutoff state. Okay, they should be in the cutoff state. Okay, so now, but how come it is possible? It is only possible when both the inputs are in the logic 0 state. Okay, so this will verify, what this will verify? One of the entries of the NOR gate of the truth table. Okay, so now if both the inputs are in the logic 1 state, okay, just imagine if both the inputs are in logic 1 state, then both the N channel devices are conducting and both the P channel devices are non-conducting. Okay, and this will produce the logic 0 at the output. Okay, so this will verify the another entry of the NOR truth table. So now for the remaining two entries we will discuss. Now if we want for the remaining input combinations, it describes that either of the two parallel N channel devices can be conducting and either of the two series connected P channel will be non-conducting. Okay, so what we will have either Q1 off and Q2 on, or we will have Q2 off and Q4 on. Okay, so the output in both the cases will be logic 0. So this will verify the remaining entries of the truth table. Okay, so this was all about the CMOS. We have discussed CMOS inverter, CMOS NOR and CMOS NAND. Okay, so this was all about the CMOS logic family. So I hope you understood the video. See you in the next video.